Okay, good evening, good afternoon, or morning, whatever applies to wherever you may be. My name is Martijn Marsman, and I'll take this opportunity to present something about the work we have done and are doing to port VASP to GPU using OpenACC. And more specifically, I'll tell you something about the way we try to use the asynchronous execution model of OpenACC. But first, let me start with a few slides on VASP itself. So VASP stands for the Vienna Ab-initio simulation package, and it's a program to basically predict how electrons behave in a material at an atomistic scale. We do this by solving the equation that governs the behavior of electrons at the atomistic scale, the Schrödinger equation at some level of approximation. And once you know this, once you have solved these equations, from this you can then deduce all kinds of interesting aspects of a material. So, for instance, whether it conducts electricity or its chemical reactivity, structural hardness, and so on and so on. I've shown here on the right a picture of one of these solutions. So this is the solution of a Hartree-Fock hybrid functional calculation. And what we see here is the predicted the probability of an electron to occupy a defect at the surface of anatas. So basically, this is something that comes out of the program, and once you know how the electrons at the surface behave, you could then deduce all kinds of interesting properties of this surface. So this is a fairly widely used code, both in academia as well as in industry, and it's developed at the University of Vienna. The group of Professor Georg Kresse, and currently also at the VASP Software company, which is a spin-off of the university that is largely owned by the University of Vienna. So the computational characteristics of a typical VASP workload consist mostly of FFTs, so relatively small FFTs, and matrix-matrix multiplication. We do a bit of diagonalization as well, and depending on, of course, of the computational setup, there's communication involved as well. And all this work is put into libraries as much as possible. So for FFTs we use FFTW or the wrappers of FFTW, so the FFTW wrappers to MKL FFTs. Well, matrix-matrix multiplication is done by BLAST3 routines, diagonalization taken from Scala part mostly, and communication is done using MPI. And a bit of OpenMP is involved as well. So VASP is pretty well characterized by the SpecFP benchmarks. And let me go on. And it has, well, organically grown for more than 25 years. So we have quite a lot of code. It's written in Fortran, some 450,000 plus lines of Fortran 77, 90, 2003, and 2008 code, mostly Fortran 90 though. And the previous releases of VASP, so which were the last one was VASP 5.4.4, previous release contained a CUDA port to GPU, so a CUDA-C port to GPU. And well, we were not so happy with that in terms of maintainability and extendability. So we have decided to report everything using OpenACC. So the current release version of VASP, which is VASP 6.1 something, contains an OpenACC port to GPU. And well, owing to the simplicity of porting using OpenACC, this OpenACC port quickly became more complete than the old CUDA port ever was. So we're quite happy with this. So a few words on the OpenACC port. Of course, we find that this solves many problems that we had with the old CUDA port. We now have a single source. Readability and maintainability are sort of guaranteed. It's still adding compiler directives still does not improve readability, but it's much better than what we used to have. Of course, as with our CPU code, we aim to put as much of the work as possible into libraries. So I've listed a few here. Of course, we have this QFFTs for the FFTs, QBLAST for the BLAST level 2 and level 3 work. CUDA-aware MPI is used, and NCCL, the NVIDIA Collective Communications Library. I've highlighted here in red because it's part of what this talk is mainly about. We have some dedicated kernels written there, so some specific OpenACC kernels added to the code. We batched some FFTs, we have reordered some loops in some kernels, stuff like that. A lot of additional programming was concerned with manual deep copies that we had to do for our nested derived types, but I don't want to go into that in this presentation. I just want to mention that we have a lot of issues with small workloads, so it's hard for us to saturate GPUs sometimes. For this, we rely on multiple ranks sharing a GPU using MPS. And the last topic that I've listed here is the use of OpenACC asynchronous execution infrastructure, and I've highlighted that in red because that is one of the things that I would like to especially mention in this presentation. So the asynchronous execution model of OpenACC and the way one can use this in combination with NCCL are basically the things that I would like to present. Oh, this slide is not complete, unfortunately. Well, okay. This slide is unfortunately not complete, but I can make do with it. So basically the main task that we do, so before I will show you some of the stuff that we have coded up, but the main task that VASP does, so the main computational task, is solve eigenvalue equations, and depending on the level of approximation to which we solve the Schrödinger equation, these are Kohn-Sham, Roothaan, or quasi-particle equations. Well, whatever they may be, that is not so important now. But the set of eigenvalue equations is of the size of the number of electrons that we have in our simulation box, and that's typically several hundreds or up to several thousands. And the work on these, we solve these eigenvalue equations for the one electron orbitals psi and the one electron energies epsilon here. And basically the work and the data that is involved is distributed over MPI ranks. So that would have been on this side of the slide, but somehow that has dropped off. So we divide the data and the work, solving these eigenvalue equations for a certain orbital gets put onto a certain MPI rank, and that rank is then responsible for doing that work on that orbital. Yes. So in the end, we end up with a lot of the core functionality of VASP looks somewhat like this. So the work that an MPI rank has to do on its orbitals is batched in batches of n, and this n is typically 4 or 8 or 16. So we have a lot of the core routines look like this. So we have loops over these batches, and inside there is some work done on a certain orbital. Then there are parts of the code where this work on n orbitals is done by a routine in a batched fashion. And then afterwards there's again loops over these orbitals with work inside. So the problem with this is that the work that is done on one orbital often leads to fairly small kernels. So that's one thing. From an OpenACC or a GPU perspective, we have a lot of small kernels. Some of the work is batched, like I said, and that is often done to maximize the performance of BLAST 2 and 3 calls inside of these routines. On the other hand, a lot of these steps that are done inside the loops, they're portioned this way to respect the cache coherency on Xeon-like hardware. So that is done for a reason. But if you would go to an OpenACC version of this, then you would, of course, you would make this into a parallel loop. And like I said, you would end up with many small kernels. In case of these batched routines, you would probably, and that is what we've done most often, you would, it pays off to write a specific OpenACC version of this particular routine. And that's a good thing. So where this work is already in batched routines, that is very easily exploited in OpenACC as well. The problem with having many small kernels is that it takes some time for the CPU to start up each kernel. And we try to hide that time actually by putting subsequent kernels, put these kernels into subsequent asynchronous queues of the OpenACC execution model. So that is, we have a loop variable I, and we set the queue to be I, and then we submit a particular kernel into this asynchronous execution queue. And we do that inside of this loop. So we have n queues that are being fed with some work, and afterwards we have to wait until everything is finished until we can continue. And this way we try to hide the launch latency, because the CPU is then not blocked by a running GPU kernel, and it can proceed to enqueue the rest, and that avoids some synchronizations, and it hides the CPU launch latency behind kernel execution. Or, unfortunately, vice versa, when the kernel runtime is very small. So if we look at a profile of this, we see here, for instance, FFTs on 8 orbitals. They are being launched by the CPU, so this takes some time, and then the next one is launched, and the next one, and the next one. And we see that they're put in subsequent streams. That is what we see here. There's 8 streams that get some work on the GPU. And unfortunately, we see here that this little bit of work that the GPU has to do associated with this FFT doesn't take more time than it takes the CPU to launch the next kernel. So here, effectively, the kernel execution is hidden behind launch latency. So it's something that is connected with small workloads. Yeah, that is something that we face. So the next operation onto these orbitals is then put by the next routine. In this case, it's a point-by-point product with something that gets put into the same asynchronous execution queues, and that avoids then synchronizations going from one routine, subroutine execution to the next. So we try to structure the whole code basically that way, or relevant code paths. Well, there's one exception you will see here, and that's one of these batched routines. There's a synchronization point here. There it waits, and this batched routine is then executed in a single stream. And one could even put the batched work into separate streams, but that turns out to be disadvantageous because it's better to have one large kernel than, again, go to launching several small ones. So, like I said, in small workloads, the work gets hidden behind the launch latency, but if you go to a sufficiently large workload, then we'll see that the CPU launches take some time, but the work that is being done on the GPU associated with it takes a lot more time. And in that case, the next launch is hidden by the ongoing work of the previous launch, and so on, and so on. So basically, this whole thing works as long as the workloads are large enough. So this model of trying to hide launch latency by submitting independent kernels into subsequent asynchronous execution queues works, and we see a typical gain of something like 20 to 30% for our standard electronic minimization algorithm. So that's pretty good, and that is even though often kernels hide behind the launch overhead and not the other way around. Well, this problem that we have with small workloads, we have another idea how to get around that, and that would be to hide the launch latency by means of OpenMP. basically to use OpenMP to get something like concurrent kernel launches, and that is sketched here. So this loop over this batch of orbitals becomes an OMP parallel loop, and then the hope is that submitting these kernels into the queues would happen in parallel. And unfortunately, this does not work yet. So the current CUDA driver serialized the kernel launches inside the OMP parallelized loop. So the idea is nice in principle, but doesn't work yet. So it's something to keep in mind for the future. So another way that we make use of asynchronous execution in OpenACC is by hiding collective communications using nickel behind work. So one of the heavy algorithms in our code is structured a bit like this. We have work going on, and so FFPs and stuff like that going on inside an execution Q1 on data that is stored in buffer 1. And when that work is done, then communication is started, in this case non-blocking collective communication using nickel, in this asynchronous execution Q1 of the data in buffer 1. So that gets started here, and then we switch to another buffer and we do work in execution Q2 on data in buffer 2. So once that is finished, we start the communication in that particular queue. At that time, the algorithm switches to the other queue, and hopefully the collective communication has finished there, and it can go on to do some more work. So that was programmed before already with non-blocking MPI calls, and nickel. So it's very straightforward to use nickel for this. That's almost a drop-in for the MPI calls that we had. So we had MPI non-blocking broadcast and await at some point, and that is basically a nickel broadcast and a wait for the queue to finish, because in the nickel broadcast you can put the work into one of these asynchronous execution queues of OpenACC. So that is very straightforward to use, and it works quite well. That is shown in this particular profile. So here, this little sliver of blue that you probably hardly see, that's the GPU that starts a broadcast and then goes on to start work on data in a different buffer. And here we see the work that the GPU has to do for this nickel broadcast. And that gets almost completely or perfectly overlaid by work that is going on the data in the second buffer. So this is this is a profile for one single node. So this communication is on-node communication, which is quite cheap, but there's still a lot of headway here because this execution of this particular part takes 6 seconds, and this is the communication here takes half a second or something. So we have good hopes that for multi-node behavior, this will still, this overlap will still be substantial, and I'll show you some data on this. So basically, the on-node behavior, if you so want, is shown here, and this is for a particular hybrid functional calculation, something like 250 atoms and 1,000 electrons. It's quite heavy for hybrid functional calculations. And we see that we have very good speedups from 1 till 8 V100s. We see speedups going from 5 to roughly 30. So this is pretty good. But that is on node. So we have the same stuff we have done for the multi-node jobs. And basically you see how well communication remains hidden in this line here below. Because this line here below is the line where we have 8 V100s, so 8 GPUs in total. But here they're on one node, here we have 4 GPUs on 2 nodes, here we have 2 GPUs on 4 nodes, and here we have 8 nodes with 1 GPU. And we see that the execution time does not change at all. So communication over the network remains completely hidden behind the work that is going on the GPUs, like it was for the single node behavior. And when we then go to these other lines, where we see basically we go from 1 to 2 to 4 to 8 nodes with 8 GPUs per node. So here we have 64 GPUs at work, and we see that going from 8 to 16, it's almost perfect scaling still. Here going to 32 GPUs, scaling parallel efficiency is still at something like 90%. So this is working really, really well. Actually, at some point, parallel efficiency drops off, and that is basically a sign that we do not have enough work per GPU or per rank anymore to hide the communication behind. Yeah, so this brings me to my conclusions. We had 2 problems. We have many small kernels that we tried to combat with this asynchronous execution by submitting identical independent kernels into subsequent asynchronous execution queues. Well, we do hide CPU-sided launch effort behind kernel execution for large jobs, but for small workloads, it's the other way around. We still have some hope that at some point we can use OpenMP plus OpenACC to battle the second condition, so small workloads. And of course, we know that batching small kernels in specific OpenACC routines would be better performance-wise, but it would be much more work and it would be much more invasive. And the other topic that that is related to asynchronous execution was hiding collective communication. So we use Nickel as a drop-in for non-blocking MPI collectives and overlay computation and communication explicitly by putting them in their own asynchronous execution queues. And this works really, really well, both on and across nodes. Well, if you so want, the drawback is that there's an additional library dependency, of course. So we rely on Nickel for this. Another thing is that we cannot use Nickel to have ranks communicate with each other that share a GPU. So this is an issue for us for small workloads because their single MPI ranks are often not able to saturate the GPUs. And another thing that remains a question maybe is, well, for Nickel, well, NVIDIA hardware is covered, but what about other GPUs? So those are essentially my my conclusions of this talk. And with that, I would very much like to thank the people that have made a lot of this possible: Steven Mines, Alexei Romanenko, Andreas Hein, and Markus Wettstein from NVIDIA and PGI, and from some people of the EFPN, Ani, Ancio Sedrakian, and Thomas Guignon for working with us. And thank you for listening.